today we will finish up the chapter 4 on Hermitian and symmetric matrices. Hermitian and symmetric matrices. Yeah, we had the motivation of Hermitian matrix, such as Jacobian matrix and quadratic forms. And we had the definition and properties and characterization of Hermitian matrices. And we had covered the variational characterization of eigenvalues of Hermitian matrices, such as inner-racing properties of inner-racing properties of eigenvalues of matrix and its submatrix or its bordered matrices. And some applications of variational characterization, such as Leach, Fisher coefficients, etc. Today we will start from majorization. Okay, majorization. Okay. Definition. Definition of the majorization. When we have two vectors in Rn, alpha and beta, we call a vector alpha is majorized by beta, and we write in this way. Alpha is majorized by beta if minimum of summation of beta ij from j1 to k is greater than equal to the minimum of summation of alpha ij from j is equal to 1 to k for all k from 1 to n, with equality for k is equal to n. What this means is, if we give an order in the entries of vectors alpha and beta with increasing order, then we give an order of increasing for two vectors alpha and beta, then what this condition says is this. Alpha is majorized by beta if and only if summation of aj from I equal 1 to k is less than or equal to summation summation of beta mi from I is equal 1 to k for all k, with equality for k is equal to n. What this means is, if we just discard the first index, then A1 is bigger than, less than or equal to alpha 1 is less than or equal to beta 1, and also alpha 1 to alpha 2 is less than or equal to these two, and alpha, this order is preserved until very last one. Particularly when you reach it to the end, this inequality is changed to an equality. This is the condition for the majorization. Okay. Chong, you understand? Jiwan? Okay. So this is very interesting properties. In 1923, Ch4 gave a following theorem, 4.3.26. For an Hermitian matrix A, Hermitian matrix, so it has all eigenvalues that are real numbers. Okay? The main diagonal vector of A, which means A11 and A22 and ANN. Okay, this let's make it this as a vector. Okay, the main diagonal entries of that Hermitian matrix. Let's say this is one vector, and consider since this is an n by n matrix of Hermitian, okay, so it has n eigenvalues and real eigenvalues. So we have n real eigenvalues. We form a vector of eigenvalues. Okay. Then we found this vector majorize this vector. That's what Ch4 found in 1923. The proof was made by mass induction in the dimension. When n is 1, when we have a 1 by 1 matrix, it's trivial. So we have one eigenvalue and one eigenvector, eigenvalue. So there's no doubt. There is a, because they are equal, so actually its majorization is preserved. Okay, but so assume true. The statement is a statement true for all k, which is less than or equal to n minus 1. Now we show the statement is true for n. Okay. Let A1 is a submatrix. N minus 1 by n minus 1 submatrix of A. By choosing n rows, n minus 1 rows and n minus 1 columns from the matrix A. Okay. By deleting the row and column that has a maximum value of eigenvalue. Okay? When you have A11 here and ANN here, we delete one row and column that has the maximum AII. We delete maximum. We delete the ith row and we delete a row and column that has a maximum value among the main diagonal entries. Okay, then we can give an order on the set of eigenvalues, the spectrum of A, with increasing order. Okay, so we have the n by n matrix, Hermitian matrix A has n real eigenvalues. So we arrange it in increasing order. And this submatrix, n minus 1 by n minus 1 submatrix A1 has n minus 1 eigenvalues. Okay, this is also a Hermitian matrix, so it has all real eigenvalues of n minus 1. So we give an order, we arrange it in the order of increasing. Okay, then, and that give an order on the main diagonals in the increasing order. Then, by the induction hypothesis, we know the eigenvalues is majorized by the main diagonal entries. Okay? Okay, then we recall the inner racing theorem for the bordered matrix. When we have a matrix and we just add one more row and column, then the eigenvalue structures have an inner racing property. So the eigenvalues of A is bordered matrix A and submatrix A1 has these properties. The eigenvalue appeared in between. So the summation of those eigenvalues have the inner racing properties. I think this is an errata. Okay? One, this one should go on. Yeah. This errata. So these eigenvalues satisfies this equality. Then these eigenvalues is majorized by main diagonal entries. And at final, it is the equality holds when k is equal to n, because trace of A is same as summation of all eigenvalues. It concludes the proof. So it is majorized. So we have shown the set of eigenvalues is the eigenvalues is majorized by set of main diagonal entries by mass induction. This is what this theorem says. Very interesting fact, which was shown in 1923. Yeah. The set of eigenvalues is majorized by set of main diagonal entries. Very interesting. So majorization is also very useful in expressing the relationship between the eigenvalues of a sum and those of its summand. Other interesting fact is about summations. This is what it says, those of its summand. For the Hermitian matrix A and B, addition of eigenvalue of A plus and eigenvalue of B is majorized by the eigenvalue of A plus B. This is the things that we can think, and it was shown. It is really true. Let's think for arbitrary k. If you arrange the eigenvalues of A and B and A plus B in the increasing order, then the summation of eigenvalues of A plus B from I is equal to 1 to k is the minimum of trace of U star A plus B U, because eigenvalues is preserved by unitary similarity with the restriction on the unitary similarity. Okay, and then this can be written as this, because just trace of U star A plus B U can be written as trace of U star AU plus trace of U star BU, and this we can split it by two pieces with the inequalities. Then we can easily see those are same as summation of lambda I of A plus summation of lambda I of B. And we can combine those two as one. And this inequality holds if we have eigenvalues in the increasing order. And when k is equal to n, we have the equality. So it just satisfies the condition for the majorization. So we have the set of eigenvalues with the increasing orders. Increasing order. Okay, so this is pretty much interesting fact that we can use. And corollary. When n is greater than or equal to 2, and alpha i's is arranged in the increasing order, and beta i's is arranged in the increasing order. In that case, if beta majorizes alpha, so alpha is majorized by beta, then there exists a gamma. There exists the vector gamma, which consists of gamma i's, such that gamma I is in between of alpha i's, and beta, and also there is beta prime such that gamma is measured by beta prime. Actually, this is lemma. It's not a corollary. The reason that we show this is to have this. That lemma will be used to have. If alpha is measured at beta, then there exists a double stochastic matrix S such that beta is equal to that matrix times alpha. The lemma will be used to get this one. This is very important. If so, here we have a condition for the majorization, but it's hard to use this condition when you to proceed our argument. But from here, we can replace beta with S alpha in our argument. So we can proceed without much difficulties. That's why we had this lemma. Anyway, let's give some more thought on the geometrical meaning of majorization. A matrix A, non-negative matrix, non-negative Lie matrix A, is called doubly stochastic if the row sums are all ones for each rows and column sums are all ones for each columns. Then we call that non-negative Lie matrix is doubly stochastic. Row stochastic and column stochastic. So if it holds both of two conditions, then we call it doubly stochastic. And we can recall Birkhoff theorem that says if the non-negative Lie matrix A is doubly stochastic, if and only if that matrix A is a convex combination of finitely many permutation matrices. Doubly stochastic matrix is a convex combination of finitely many permutation matrices. This was proved by Birkhoff. Okay. So anyone recall that who is the name of Birkhoff? G.D. Birkhoff and Garrett Birkhoff. You don't remember? Yeah, I talked about the history of American mathematics. That E.H. Morse had a brilliant student. The first one was Ellie Dixon. Second was Oswald Veblen. Third was R.L. Moore. And fourth was G.D. Birkhoff. And son of G.D. Birkhoff is Garrett Birkhoff. Okay, anyway. So the set of n by n non-negative Lie doubly stochastic matrix. This set of these matrices is denoted as omega n. So omega n is the set of non-negative Lie doubly stochastic matrices of the size n. Okay. Then we can have a better theorems, such as theorem 4.3.32 and 4.3.33. Let's see. If that n is greater than equal to 1 and ai's are arranged in the increasing order and lambda i's are arranged in increasing order, then vector A majorizes lambda, and lambda is majorized A. So this is the lambda i's, and here A1 and AN. Okay, this is notation for this. Then there exists a Lie symmetry matrix A such that AII is equal to AI, and spectrum of A is lambda i's, set of lambda i's. So if A is if lambda is majorized by the vector A, then we can construct a Lie symmetry matrix A whose eigenvalues are lambda i's and main diagonal entries are AII, which is AI. With that, that's easy. It's an easy proof on it. Yeah. Okay. From that, we can show this main theorem that will be used over and over again. That alpha and beta are n-dimensional Lie vectors. Then the following are equivalent. Alpha is majorized by beta. If and only if there exists a doubly stochastic matrix S such that beta is equal to S alpha. If and only if the beta is in the set of summation pi alpha pi I, where n is between 1 to infinity and pi is positive real numbers, and summation of pi is equal to 1. Here, alpha pi I is a vector whose component are some permutation of component of a given vector alpha. In here, the important part is this. Important part is that when you have a relationship of majorization, then you can always replace one with others. With doubly stochastic matrix. Then it will make the process much easier when you continue your argument. Okay, here's one example. Let x and y's are n-dimensional vectors in Rn, and x is measured by y, then show the product of yi's is greater than or equal to product of xi's. We know the summations are equal, isn't it? But product is different when you have a non-negative. Okay, proof. By the previous theorem 4.3.32, there exists a real symmetry matrix A such that AII is equal to YI and the eigenvalues are XI's. Then A is a positive definite symmetric matrix. What that means, because all the eigenvalues are non-negative. These are positive semi-definite. Positive semi-definite. If xi is all positive, then we can say that's positive definite. If xi's are all non-negative, then we can only say it is a positive semi-definite matrix. Then, by the Hadamard inequality, if A is a non-singular, then it is positive definite. If it's non-singular, then it is positive definite. If it's singular, then it's equal. It's zero on both sides. It's non-singular, it's positive definite. So, if it's singular, then it's equality hold. If it's non-singular, it's positive definite. If positive definite, then we can have this. This is the Hadamard inequality. Hadamard inequality that you will see. This is a Hadamard inequality that you will see in chapter 7 on the positive definite matrices. If A is a positive definite matrix, then determinant of A is always less than or equal to the product of main diagonal entries. This is Hadamard inequality. So by this, since these are the eigenvalues, so product of eigenvalues are determinant, and this is the product of main diagonal entries, and the main diagonal entries of that matrix A are yi's, so that has this kind of relationship. So this is just another nice property that we can easily draw. Okay. So my definition. Semi-definite is not semi-definite는 아이겐밸류가 이제 0일 수도 있다는 소리거든요. 0인 게 있다는 소리죠. 0인 경우는 따로 처리를 하는 거지. 따로 처리하는 거지. 근데 이 경우는 이거는 한쪽은 그러니까 예를 들어 아이겐밸류가 0이라고 하면 이쪽은 0이어도 이쪽은 0이 완전히 아닐 수가 있지, 스트릭트리. 그렇죠? 그러니까 싱귤라가 나와도 대각선 성분은 다 포지티브일 수도 있죠. 어쨌든 하다마트 이니퀄리티는 퍼지티브 데피니트에 대해서 성립한다는 얘기니까. 거꾸로 가는 경우도 있을 수가 있을 겁니다. 왜냐하면 이게 포지티브 세마이 데피니트인 경우에는 싱귤라인 경우잖아요. 싱귤라인 경우에는 이쪽은 0이 있죠, 이쪽은. 근데 이쪽은 네거티브가 나올 가능성이 언제나 있죠. 싱귤라인 매트릭스는 대각선 성분에 뭐 플러스 마이너스가 같이 들어가 있을 수 있습니다. 그러니까 그 경우에 성립하지 않아요. 그러니까 포지티브 데피니트인 경우를 따로 생각하고 싱귤라인 경우 따로 생각하면은 그러면 우리가 원하는 결론을 얻을 수가 있었던 겁니다. 자, 여기서 이 미니멈을 이용한 정의 4.3.24는요. 이것은 이 x가 when x was measured by y, it preserves these orders. The Marshall and Olkin wrote a major reference book on the majorization. In its book, in their book, they use the maximum instead of this minimum definition. In that case, we have to follow when x is measured by y, then the vectors has different orders like this. So Charlie Johnson and Roger Horn adopted the minimization definition on the majorization that has a better presentation like what we see. So this is an improvement of the previous argument and logics. Okay, any questions on the majorization?